Assalamu alaikum, my dear students. Welcome back to our Mathematics 2 tutorial. Today we are starting a new series of exercises on chapter 2. In this video, we'll solve exercise number 1 step by step. Let's look to our problem. We have a map F defined from R3 to R2 given by the following formula. Our goal is to explore its fundamental properties, linearity, the kernel, and the image. The first question asks us to verify that F is a linear map. Let's do a quick reminder. A map is linear if it preserves vector addition and scalar multiplication. This means that the image of ax plus b times y equals to the sum a f of x plus b f of y, where a and b are two real numbers and x and y are vectors. Let's prove this for our map. Let our vector x, y, z and x prime, y prime, z prime and a and b two real numbers. We start by calculating f of ax plus by. First, we group the components inside the function. Now we apply the definition of our map. The first component is the first variable plus 3 times the second variable. The second component is twice the first variable minus the third variable. Next, we separate the terms with a from the terms with b. And look at this. This is exactly a times f of x plus b f of y. Therefore, f is a linear map. Let's move to question number 2. We need to find the kernel of f and its dimension. As a brief reminder, the kernel of f is the set of all vectors in the starting space that map the zero vector of the arrival space. And we can write the kernel of f is equal to the vector x, y, z, such that the image of this vector is the zero vector. By replacing f of x, y, and z with its formula, we get a system of equations like this. From this system, we can express y and z in terms of x. We find that y equals to minus 1 over 3x and z equals to 2x. So any vector in the kernel can be written as x multiplied by the vector 1 minus 1 over 3 and 2. This means that this single vector spans the kernel. Because this vector is not the zero vector, it forms a linear independent family. Therefore, it is a basis for the kernel. And we can write the basis of the kernel of f is the vector that we found previously. Then the dimension of the kernel of f is equal to 1. This brings us perfectly to question number 3. Remember the rule. A linear map is injective if and only if its kernel contains only the zero vector. We just found that the dimension of the kernel is 1, which means the kernel is not just the zero vector. Therefore, f is not injective, and we can write it like this. For question number 4, we need to find the dimension of the image of f. To do this quickly, we will use a very famous theorem, which is the rank nullity theorem. It states that the dimension of the starting space, which is the dimension of R3, equals the dimension of the kernel plus the dimension of the image. We know the dimension of R3 is equal to 3, and we found the dimension of the kernel is 1. So the dimension of the image of f is equal to 2. Now, what is a basis for the image? We know that the image of f is a subspace of R2, and the dimension of the image of F is equal to the dimension of R2, which is 2, then we can write that the image of F is exactly R2. Therefore, we can simply use the standard canonical basis of R2 as our basis, and we can write the basis of image of F is the vectors 1, 0 and 0, 1. For question number 5, is F surjective? Remember, a map is surjective if its image is equal to the entire arrival space. We just proved in the previous step that the image of F is equal to R2. Therefore, we can conclude that F is surjective. And with that, we have completely solved exercise number 1. Thank you for watching and see you in the next video for exercise number 4.